This is the setup solution for problem number 58 for free body diagrams. So I've got two blocks, one on the table and one that's hanging. The one on the table is the free body diagram on the right. Because there's a surface, the block is sitting on a surface, there's a normal force. There's a rope pulling it to the right, so the tension goes pulled to the right because you can only pull with a rope, you can't push with it. Because it's trying to be pulled to the right, there's friction opposing the motion on this particular part of the problem. So friction goes to the left opposing the motion. And then I've got this weight going down. And I've labeled it W subscript 100. And I use the W subscript 100 because it's a 100 Newton weight. So for both of these weights, the 100 and the 50, I just put a subscript 150 when I'm doing the math to remind me what I have. Typically on these problems I write mg, but since they already did the math for me and told me it's 100 newtons, that's why I wrote it as W subscript 100. The right hand side is the weight that's hanging off the table, so I've got a tension pulling that one up, and then I've got the weight going down. Next step is to establish a coordinate system. So I'm going to choose just a regular x and y, so parallel to the surface and perpendicular to the surface for the block that's on the incline. For the hanging block, I'll just choose up and down along the tension, and left and right really doesn't matter because there isn't any forces, or there aren't any forces left and right. Same with the forces for the block on the table. I have the sum of the forces in the x direction, and remember when I'm looking for this math sentence to say the sigma, the f, and which direction you're looking at. And that's equal to 0, and it's equal to 0 because it's not accelerating. And that equals all the forces to the right minus all the forces going to the left. So tension minus friction. Do a little bit of math and I get friction is equal to tension, and that's as much math as I can do with that statement. Sum of the forces in the y direction, well, it's not accelerating in the y direction either, so it's equal to 0. Again, I'm looking for this math sentence. I'm looking for the sigma, I'm looking for the force, the capital F, and the subscript y telling me the direction that you're looking at. And then it's got to equal whatever the net acceleration is. In this case it's 0. Then that's going to equal all the forces going up minus all the forces going down in the y direction. So if I do a little bit of math, I get eta is equal to the weight of the 100 newtons. So eta is equal to 100 newtons. For the hanging weight, I know the sum of the forces in the x direction is equal to 0 because there are none, but even though it seems like you don't need to state it to address the fact that you've looked at this and you realize there's nothing there. And then summing up the forces in the y direction, again, the sigma, the f, the subscript y, it's equal to the net force, which in this case is 0, because it's hanging there, it's not accelerating. And that's equal to all the forces going up minus all the forces going down. So that's tension minus W subscript 50. So therefore the tension is equal to W subscript 50. Or doing a little bit more math, tension is equal to 50. So now with these blue equations, I can start to address what the question is actually looking for. The one equation that's not up here, which is helpful, is the fun equation. Friction is equal to mu times eta. That can help us solve this problem as well.